Hey everybody, this is Mr. Brooks again. So, in case you forgot that it was me. So this is section 4.7. So we've just covered complex eigenvalues, and so now we are going to get into the very last part of this, which is repeated eigenvalues. Now we are going to be very limited on what we do here just because of the nature of the problems. However, we're mostly going to focus on what to do when we have a 2 by 2 matrix, but we will talk about in general what happens for these and a process on how to find more solutions, because that's the main crux of the problem when we're dealing with these guys. So if an n by n matrix A has a repeated eigenvalue, and we'll call that lambda again, then the number corresponding to the eigenvectors varies. Okay, so this is what happens when we have repeated eigenvalues. So what we're going to get into is, so this is a little bit different from how the book approaches it. It deals with a few examples first. So we're going to get into the main definition, so then that way we can talk about it a little bit more, give some examples, and go on from that part. So what we need to look at is what we call the algebraic and the geometric multiplicity. So algebraic is pretty straightforward on what it means. The geometric property comes in when we're talking about the eigenvectors themselves. So let's get over with these definitions so that way we can see what we're talking about. So first of all, the beginning of the definition is we're going to let lambda be an eigenvalue for some matrix A. All right. And so the algebraic multiplicity, okay, that was a smaller writing than I thought it was going to be. So algebraic multiplicity of lambda is of the order of lambda as a root of the characteristic equation P of lambda is equal to 0. Okay, so what that means, an example of this, is if we say that P of lambda is equal to, and here this is where we're going to get into the repeated part, lambda minus alpha, where alpha is one of the zeros, and it's repeated r times. And I am going to introduce a slightly new piece here, this q, but we're going to talk about it. Here, this q, where q of lambda is another polynomial of degree n minus r. So what this is saying is we've pulled out this factor that's been repeated from the polynomial p, and we're left with the multiplication of some other polynomial. So that's all this is. It's like as if we understood what the with synthetic division, if we know we have one factor, when we use synthetic division, then we know the next polynomial, that's the next polynomial in this piece. So that's all this is. And q of alpha is not equal to 0. So what it's just saying is this alpha is not a 0 of the polynomial p, or polynomial q. So that means we've pulled every single thing out of it, because if it was, then we'd have another factor that's involved. Then alpha is an eigenvalue, because again it's coming from our characteristic equation, of algebraic multiplicity r. So what it's saying is how many times this has been repeated. That's what the algebraic multiplicity is once we get a 0 for the eigenvector, how many times was it repeated? That's its algebraic multiplicity. So when we talk about multiplicity, it's the same thing as what we did if we were dealing with any type of polynomial function and talking about how many zeros that it had and if they were repeated. Okay, next is going into the geometric multiplicity, and I'm going to try to do this in green to separate it a little bit. The geometric multiplicity is a little bit harder concept to talk about, but it's not that bad once we get into how we approach it. So the geometric multiplicity of an eigenvalue lambda is the number of linearly independent eigenvectors that can be found corresponding to this lambda, okay, to this eigenvalue. So that's what that means. Now, a cool couple notes that comes from this. So again, a geometric is the number of linearly independent eigenvectors associated with the eigenvalue. Algebraic multiplicity is the number of times it was repeated from the characteristic equation. Okay, some notes that we want to make about this, and we have talked about this before. A matrix A has a full set of eigenvectors. So remember when we talked about full sets before, full sets were when, and this is coming from 4.5 if I'm not mistaken, a full set of eigenvectors means that they are linearly independent and there's an n number of them. So that's what that means. And the cool part is if the geometric multiplicity, GM, is equal to the algebraic multiplicity. So if we can find that say we're repeated 10 times, and I'm not going to say that we're going to deal with one of those, but if we had the eigenvalue repeated 10 times and we had 10 associated eigenvectors to go with it that are linearly independent, then we could say that the matrix has a full set of eigenvectors. Now the next thing that comes out of this is we've talked about it being defective before. A matrix A is defective if A has one eigenvalue with the geometric multiplicity is less than the algebraic multiplicity. So the only time that when we're dealing with geometric will either be equal to or less than the algebraic in multiplicity. And it's also the highest it will go is if you have an n by n matrix, then you'll have at most a multiplicity of n and a geometric multiplicity of n in that case. So if it was a 3 by 3, then the most that both of these could be is 3. If we had a 10 by 10, it would be 10. Okay, so it's not going to go past that number. So defective means it does not have a full set of eigenvectors, which means we're missing at least one or more eigenvectors to make a full set of linearly independent eigenvectors to come up with a fundamental set in the end. So our process through this point is going to be talking about, okay, how do we calculate these, or what is the approach for finding out if the geometric multiplicity is equal to the algebraic, and then say, okay, well, if that occurs, if they're equal, it's great. Things work out for us because then we've seen repeated before in section 4.5, and we're able to deal with them because we had different linearly independent eigenvectors to go with those eigenvalues, and so we could come up with solutions of that form. So now we're going to be looking for a new eigenvector that we need to make sure that is linearly independent. And so there is a process that we are going to go for with 2 by 2s that can be extended for that. Okay, so let's look at the following. Here I just want to see what their eigenvalues are and what the multiplicity is, and then also what their algebraic multiplicity is, and then also find out what their geometric multiplicity is. And so this is coming from the book, but this is really 3 good examples, and I'm going to go through the process of finding your eigenvalues and the eigenvectors and walk through it. All right, so with A1, we have a matrix that is 2, 1, 0, 0, 2, 1, and 0, 0, 2. Okay, so in order to find its eigenvalues, we're going to find the determinant of A1 minus lambda I, which is equal to the determinant of the following matrix, which is 2 minus lambda, 1, 0, 0, 2 minus lambda, 1, 0, 0, 2 minus lambda. Okay, in the end, when we multiply this, I'm going to use, to find the minors, it doesn't matter which one you use for this part, but I'm going to use the minor of the bottom row here because it's all zeros except for this 2 minus lambda. So I'm going to get 2 minus lambda times its minor, which is 2 minus lambda times 2 minus lambda minus 0. So in the end, we get 2 minus lambda, quantity squared. And so we set this equal to 0. I'm going to do a little bit of factoring, multiply this guy in, so we're going to repeat this 3 times. I am going to pull a negative out. So I'm going to get lambda minus 2 cubed is equal to 0. So that means lambda is equal to, make sure I have enough room, yeah. Lambda is equal to 2 with am equal to 3 because it's been repeated 3 times. So this is the algebraic multiplicity of this particular eigenvalue. So let's find the eigenvector and talk about its geometric multiplicity. So with lambda is equal to 2, we plug that back into our matrix here of a minus lambda I, and I'm going to get 0, 1, 0, 0, 0, 1, 0, 0, 0. And we're going to multiply that again by our vector here, which we're trying to find. That's supposed to be just x of 1, x of 2, x of 3, set equal to 0, 0, 0. All right. So when I multiply this, notice what the relationship is that x2 has to equal 0. x3 has to equal 0. Because when we multiply this, we're going to get x2 is equal to 0, x3 is equal to 0, and x1 can be any value. Which means x, the eigenvector associated with this, is of this form, x1, 0, 0. Now another way that we could write that, and I started doing this process on the previous lecture as well, so this is a good way to come up with these, is that x1, if I factor it out, that becomes, and let me write that as a cursive. Okay, so this is a singular value, it's not a, so constant value. We'll say scalar, so that makes it a little bit more clear on that part. And so we left with 1, 0, 0. So in the end, this can be written, and I'm going to say let, just to help with this, let x1 equal a. So a times the bolded x. So this bolded x here is our vector, our eigenvector. All right, so how do we get into multiplicity? Well, notice this means my eigenvector is unchanged. Yes, it is a constant multiple of it, but think about what geometric multiplicity is. Geometric multiplicity is talking about the number of linearly independent vectors. Well, if they're scalar multiples of each other, they're not linearly independent. So the geometric, and I'll write this one out. We can use GM here. Multiplicity. And just as a reference, I'm going to put GM here in parentheses because I'm going to use this later on. Of lambda is equal to 2 is 1. And the reason for this is that since constant multiples are not linearly independent. Okay, so this is what the multiplicity part is. So let's look at another one. So the nice thing is all three of these matrices that I've written up at the top, or actually that we're about to go through, have the same lambda, but I'm going to show that too, so I'm not going to shortchange you on that piece. Okay, so moving on. So number 2. All right, I'm going to take the determinant of a2 minus lambda I. So this should start looking familiar. All right. So we multiply. I'm going to use, again, it doesn't matter in this case because I get a lot of these now. I'm going to use my bottom row again to come up with this. So 2 minus lambda times 2 minus lambda, the quantity squared. So that's going to give us our negative 2, or lambda minus 2 cubed is equal to 0. So lambda is equal to 2. AM of this particular one is equal to 3. So again, multiplicity 3. All right. So let's go through the process. I'm going to plug this back in. So I'm going to get 0, 1, 0, 0, 0, 0, 0, 0, 0, multiplied by my x1, x2, and x3. You're like, well, that doesn't even look any better. And you're right, it does not look much better, but there's actually a nice piece that comes from this. So when I multiply through here, I'm going to find out that x2 has to equal 0, because if I multiply this first row times the column and set it equal, I get 0 out. With the other ones, x1 and x3, these guys can be any value. And here we want to make sure that they're any value not equal to 0, because if they're equal to 0, then we have a non-trivial, or we have a trivial eigenvector in that case. So we want to avoid that. So that means then x for this particular case is equal to x1, 0, x3. All right, here I'm going to, so since x1 and x2 can be any value, I'm going to make x1 equal to a and x3 equal c. So notice a, b, c. Here b is equal to 0 and it's forced to be. Well, there's a way I can write this, and this is a good way to come up with these eigenvectors a little bit easier when you're working through these problems with regular, where they're not repeated or anything. But if you get this relationship, it's easy to build these guys. So here, if I did a times 1, 0, 0 plus c times 0, 0, 1, notice I will get back to this a0c vector, which means this is a times one eigenvector plus c times another one. And 1, 0, 0 is linearly independent from 0, 0, 1. So lambda is equal to 2 has a geometric multiplicity, of 2, because we have two associated eigenvectors that are linearly independent of each other. Okay, so x1 is independent of x2. Okay, and here again trying to do bolded ones to represent the eigenvectors for that case. So that's what that means. So let's move on to the third one. Okay, so we have an even simpler one that's going on here. And this one's actually really fun too. So again, the determinant of a3 minus lambda I. And again, so one thing I do want to, and I'll clarify this here. So that means the first and second examples are what we call defective matrices because they do not have a full set. They're missing, the first one's missing 2. The second one is missing 1 eigenvector that's linearly independent. So we have to still find those guys. All right, so we get 2 minus lambda, 0, 0, 0, 2 minus lambda, 0, 0, 0, 2 minus lambda. And its determinant is, again, now we can multiply, find it through any row or column for this that we choose. And we find out that it's negative 2 minus, or lambda minus 2 cubed is equal to 0. So lambda is equal to 2. And the algebraic multiplicity is equal to 3. Again, how many times it was repeated. All right. So with this one, when we plug back in our lambda of 2, we get 0, 0, 0, 0, 0, 0, 0, 0, 0. I go, well, great. Well, there's a cool thing with this one. This means when we have a 0 row or 0 matrix in this case, any non-zero, again, we don't want this to be a trivial case. So any non-zero vector is an eigenvector of A3. And you can test that. Pick any three numbers that you want for A1, A2, and A3. We multiply it by the zero matrix here. We're going to get zeros out. Okay, that's the cool thing. So thus, lambda is equal to 2 has a GM equal to 3. So this would mean that it has a full set of eigenvectors. And we should already known this as well, because when we go back to 4.5, when we talked about a matrix that you could, the transpose is equal to its original, we could say that it has a full set of eigenvectors as well. So that's the cool thing about this. We already knew that this was coming into play, but the nice thing is we also found out, because of the associated x1, x2, x3, where we could pick any value, we could choose any. Well, this means there could be an unlimited amount, but our geometric multiplicity is only as large as the algebraic multiplicity. So since it was 3, we have 3. All right. So in each of these examples, we have the geometric multiplicity either less than or equal to the algebraic multiplicity. And okay. All right. In 1, we need to find 2 more solutions, or 2 more eigenvectors to form a fundamental set. So A1 is defective. Number 2, we need 1 more. So A2 is still defective. Even though it's just missing 1, it's still defective in this case. And number 3, so A3, the GM is equal to the AM. So again, I'm going to write that too. GM strictly less than AM. So here, since the GM is equal to the AM, we can select any, and here I got to be careful, any 3 linearly independent eigenvectors and here we're going to give them U, V, and W. So by, this is coming from theorem 4.6, we have the solution. So once we have these linearly independent eigenvectors U, V, and W, then we have the solutions of y1 is equal to U, sorry, not U, e to the 2t U, y2 is equal to e to the 2t V, and y3 is equal to e to the 2t W. Okay, again, where the 2 is coming from is lambda was equal to 2. And the nice thing is we have a full set of eigenvectors. And remember, once we found out that we have a full set, we can immediately write these as, since they're linearly independent, we can write the general solution for this. All right, so this is very important. So if we can find out the geometric is equal to the algebraic multiplicity, then we're good to go. So the question is how do we find these other solutions? So I wrote that a little bit further down. So how do we do that? That's a very good question. I'm glad you asked it, because now we're going to go through an example. All right, so this is going to take some time, but it's not that bad. There's some weird things that came out of this. Now, if you're reading through the book goes through an example of if we're missing a solution, and they actually found a way to get there. I'm going to cut some of the fat off of this and go straight for a little bit more straighter path as we go through here. So I hope that helps out some. So here we're going to do this for a 2 by 2. All right. So for a 2 by 2 matrix, if y1 is equal to e to the alpha t x1 is a solution, we look for a second solution So let's say here that alpha has an AM equal to 2, but a GM equal to 1. So meaning that it's defective. So we need to look for a second solution. Well, we're going to look for a second solution of the form y2 of t is equal to te to the alpha t v. We've seen that before with repeated values before. So that's the nice thing, is this is something that's not entirely new. So we're going to say v1 plus e to the alpha t v2. All right. Here, v1 and v2, so these guys, are non-zero, constant 2 by 1 vectors to be determined. So we don't know these guys yet, which makes sense because if we knew them, oh, we'd skip a lot of this hassle here. Okay. So what we're going to do is I'm going to sub this in, because if this is a solution, we're going to sub it into our matrix, okay, or into our differential system. Okay. So substituting into y prime is equal to ay, we get the following. So on the right-hand side, so I'm going to draw the right-hand side first, and then we're going to talk about the left-hand side because there's a lot more to it. We have a times this te to the alpha t v1 plus e to the alpha t v2. On the left-hand side, we have the derivatives, because this is y prime. All right, so here I've got to be careful on spacing, and I should have done this first. E to alpha t plus alpha t e to the alpha t times v1 plus alpha e to the alpha t v2. Okay, so this is the derivative of this piece. This is the derivative of the first piece that associated with te to the alpha t, because we have a product rule that's popping. All right, well, let's move everything over to the left-hand side, kind of what we dealt with when we first started dealing with these systems. So I'm going to subtract everything. So I'm going to get t, and so there's going to be some simplifying that occurred here. So where I subtract the t and the alpha t, because this a is multiplied into these guys, I'm going to have t e to the alpha t times a v1 minus alpha v2. So I subtracted over to the left, is what I did. Plus e to the alpha t a v2 minus everything that has the e to the alpha t associated with it, which is alpha v2 minus v1, and this is all equal to 0 on some interval of interest from negative infinity to infinity. So t is a part of this. Okay. All right. So let's talk about it. Well, in order for this to equal 0, there's one or two things that's going to happen. That either these first terms here are both going to be equal to 0 for the same value of t, or our coefficients here, if you will, are going to equal 0. Well, let's talk about that. The set te to the alpha t and e to the alpha t Well, these guys are linearly independent. Meaning they're never going to equal 0 with the same value of t. So that means in order for the equality to hold, this a v1 minus alpha v2 and this a v2 minus alpha v2 minus v1, those guys have to equal 0. Okay, so that's what's going to happen. So again, in order for this inequality, this equality, AV1 minus alpha V2 and AV2 minus alpha V2 minus V1 must vanish. And I'll give it here, aka equals 0 for that to happen. All right. So again, we need these two situations, A minus alpha I, V1 to equal 0, and I think I made a mistake here. That's supposed to be V1 there. So yes, I did make a mistake. This is supposed to be V1 here. So make sure that this is a V1 and this is a V1. Yep, that's my mistake. I apologize. Make sure that you fix that. So I'm going to leave that in the video because that was my mistake. So again, that's supposed to be V1. This is supposed to be V1 here. So we need this to be V1. So now that makes sense. And A minus alpha I. Okay, again, the reason that we're doing that is to subtract from A. So we have to have it n by n. This is V2 has to equal V1. So this is the weird part. We've not had this situation happen before. And 4.8 actually talks about this, but we've skipped 4.8 because it's dealing with non-homogeneous. So we're just going to let that part slide for this particular example. But if you read through, it's going to talk about how some things there's an infinite number of answers that's going to occur. But we're going to kind of shortchange this a little bit. All right. So, well, look here. Alpha is our original lambda, right? Again, going back up to our description here. So e to the alpha. Alpha is our solution. Okay, alpha is that eigenvalue, which means this part here, this first equation, is simply the eigenvector equation. Which means V1 is equal to the eigenvector corresponding to lambda is equal to alpha. Okay, so that means we know what V1 has to be. That's the good part. So now we're going to consider the other equation because we've already got this one nailed down and we now know what V1 is. A minus alpha I V2 is equal to V1. So here, because of its nature, V2 is actually called a generalized eigenvector. So that's all V2 is. This is how we find out what this is coming from because we're using the original eigenvector. Therefore, once we have those, the general solution is the following. Y of t is equal to C1 e to the lambda t V1. Okay, this V1 was the original eigenvector that this is coming from for lambda, so we've already got that out of the way. Plus, now our lambda, when we're dealing with the finding Y2, which is C2. Okay, so this here is our Y1. The C2 is e to the lambda t, has the same piece, times this t V1 plus V2. And that's all that's coming from this. So that's the cool part. So this is our Y2. All right. So now, I left apparently a lot of space. Oh, nope, I didn't leave a lot of space. I left the rest of this blank. Okay. So that means you get to see my crappy handwriting and no more nice stuff. All right. So let's look at an example of this. So I want to find the general solution of y prime is equal to the matrix 2 minus 1, or sorry, negative 1, 1, 4, and y. All right. So first of all, we need to find our determinant. So again, pause the video for a second. So we're going to find the determinant of a minus lambda I. So we got 2 minus lambda, negative 1, 1, 4 minus lambda. So when we multiply these, we're going to get 2 minus lambda, 4 minus lambda, plus 1. We want this to equal 0. All right, multiplying it out, we get 8 minus 2 lambda minus 4 lambda plus lambda squared plus 1 is equal to 0. So we're going to get lambda squared minus 6 lambda plus 9 is equal to 0. Well, factoring this, notice that this is actually a perfect square, so it's lambda minus 3, the quantity squared, which is equal to 0. Okay, that means lambda is equal to 3, and it has an algebraic multiplicity of 2. All right, so let's go through and solve this. So lambda 3, just like before. All right, so when we plug it in into our lambdas, we're going to get negative 1, 1, 1, and x1 and x2 here. Okay, well, this is equivalent to saying, since this is just a negative difference, there's the negative 1, 0, 0, x1, x2, 0, 0. All right, well, if we solve this, this becomes x1, negative x1 minus x2 is equal to 0, or x1 plus x2 is equal to 0. So that's what this becomes. And x2 is equal to any value. So our eigenvector associated with this, our x here, is equal to x2 down here and negative x, and x1, which x1 is equal to negative x2. So notice how I'm writing this. Well, if that's the case, I can factor out an x2, and I'm left with negative 1, 1. Meaning, for any value of x2, this is just a constant multiple. So the GM here is equal to 1. Okay. So y1 of t, we know, is e to the 3t, because of our lambda, times negative 1, 1. Here, for our convenience, using negative 1, 1 is the easiest one. I could use negative 2, 2. Any constant multiple will work for that. So this is the easiest straightforward one that I can do, except for x2 is equal to 0. All right. So now we need to find y2 of t. Well, let's go through it. So we know v1 is equal to that original eigenvector corresponding to lambda is equal to 3. Thus, negative 1, negative 1, 1, 1. And I'm going to write here just a second. x1, x2 is equal to this v1, negative 1, 1. Okay, and just to mark where these are coming from, this is going to be our v2 that we're finding. This is our v1, and this is a minus lambda I. Okay, these are where these are coming from. Okay, so once we find v2, we will have our general solution. All right, well, again, from before, if I add this row down, so this is where you've got to be careful with this. So I've stated this before. If I add if we did an augmented, let me do an augmented matrix. And I do row 2 plus row 1. I'm going to get negative 1, negative 1, negative 1. Zeros all the way through on the bottom. And then I'm going to do negative row 1. 1, 1, 1. All right. So that means this becomes 1, 1, 0, 0 times our x1, x2 is equal to 1, 0. Okay. Well, this means that x1 plus x2 is equal to 1, and x2 can equal any value. So v2 is of the form x2, and here I have x1 is equal to 1 minus x2. So I'm getting associated with it, 1 minus x2, which means I can rewrite it as 1, 0 plus x2, 1, negative 1. All right. So here I only need one v2. So for simplicity's sake, so let me write that. Okay, so I only need one v2. So I'm going to let x2 equal 0. So what happens to this term? It goes away. So thus, v2 is equal to just 1, 0. Well, if v2 is equal to 1, 0, that means y2 of t is equal to te to the 3t, because lambda is equal to 3, v1 plus e to the 3t v2. So another way to write this, v1 we said was negative 1, 1 plus e to the 3t 1, 0. And writing this out even further, we get negative t e to the 3t plus e to the 3t, and then t e to the 3t for that bottom one. All right, so this is our function, our solution. Okay, so we need to check. Did we just create a fundamental set? So this is all right. So I'm going to take the Wronskian of our first function, y1, which was negative e to the 3t, e to the 3t, and then this function here, vector function, negative te to the 3t plus e to the 3t, te to the 3t. So let's make sure that we get a non-zero function out of this. Well, I'm going to get negative te to the 6t minus negative te to the 6t plus e to the 6t, which that simplifies down to negative e to the 6t, which is not equal to 0 for any value of t. So therefore, we just formed a fundamental set, and now we get the general solution. So the general solution is y sub t is equal to c1 times negative e to the 3t, e to the 3t, plus c2 times our negative t e to the 3t plus e to the 3t, and then t e to the 3t here. All right, and that concludes this lesson. So here again, the biggest thing is we were focused on a 2x2. We can extend this idea out to 3x3s and whatnot, but then it gets a lot more complicated as you go. So even though I've looked at the suggested homeworks as well, they're only looking at 2x2s, and on the pathways and on the quizzes, they're only looking at for 2x2s. So this is to set you up for that. So you guys will knock these out of the park when you get there. Again, the biggest thing is if the algebraic multiplicity and the geometric multiplicity are equal to each other, we already have a full set of eigenvectors and we're ready to go. If the geometric multiplicity is less than the algebraic, that means we are going to be finding one or more solutions to go with it. Since it's an n by n matrix or a 2x2 matrix that we're going to be dealing with, that means we only have to find one solution, and this is how you do it. Y'all have a wonderful day, and I'll see you for the next one.